Okay, so we are moving on to the chapter summaries for Core Pure Year 2, and we're starting with the first chapter, which, like Core Pure Year 1, is also complex numbers, but definitely much more complicated. Now, I always say this at the beginning of these videos for further maths. It is not possible for these chapter summaries to cover all of the possible ways that examiners can assess the topic, and I think this is particularly true for complex numbers. It is really important you understand everything about complex numbers, because they may ask you some unusual kinds of things with them. I've tried to cover as much as possible in this video, but it's really here to kind of summarize that playlist and be a bit of revision just before the exams. So we're going to start off by having a look at the exponential form of complex numbers. We've obviously already looked at these sort of trig forms in year 1, but we kind of refresh them a little bit here. And then we're going to look at some things to do with De Moivre's theorem as well. So to start with, there's just a different version, the exponential form of this. Not going to go into the details of where it comes from, but we say that a complex number can be equal to r e to the I theta, where r is the modulus or the magnitude, and theta is the argument of that complex number. Pretty straightforward, and you should know that already. De Moivre's theorem is this, that when you raise a complex number to a power of n, the modulus goes to the power of n and the argument gets multiplied by n. And that's quite intuitive from the way that we know complex numbers behave. And then we've got these other ones down here. You will find that you use these a lot in the kind of skills that we have in this chapter. Okay, so I'm not going to read through them. You can just see that they've got them all here. The only kind of key thing I'll point out is that the cosine is usually with plus and the sine is usually going to be things with negatives, and of course the sine is the one that has an I with it. Naturally, when you do the trigonometric form, sine is with the I part. So the first question that we're going to answer here is it wants us to write this rather complicated looking thing in fully simplified exponential form that we've got here. Well, we should be able to recognize that the numerator here looks like it can be written from its trig form into the exponential form that we've got here. I'm not going to bother factorizing out that 3. It's pretty clear to see that this is just the same as the modulus of it being 3 and the argument being 4x. So it's going to be 3e to the 4xi or 4ix, whichever way you want to do that. And that whole thing is going to the power of 5 like this one, okay? Then the denominator that we've got, we need to be a little bit careful because we've got this minus that we have. And we know that this thing can be rewritten as this. It would be 9 cos of minus x plus 9i sine of minus x, like this. So actually the argument isn't x, it is minus x. The modulus is 9, so it's going to be 9e to the minus xi, and the whole thing is going to the power of 2, like this, okay? So what we need to do now is kind of use De Moivre's theorem. So we know that this power of 5 is going to do this as 3 to the power of 5, and then the argument is going to be multiplied by 5, so instead of 4x, it will be 20xi. And then the denominator, we get a 9 squared. We then have an e to the minus 2xi because it just multiplies the argument like this. Now what I'm going to do to simplify is just 3 to the power of 5 divided by 9 squared, which is just 3. And then just using index laws really from sort of GCSE, I will do this one minus this one. So it's going to become a 20x plus a 2x, which is a 22xi. So we've got that written in fully simplified exponential form like this. Okay, the second question that we have here is we're actually going to kind of do a little show that for one of these things here. We're going to show that this one is equal to 2 cos n theta. We're going to kind of show that that is true, and I've done it with these identity symbols here. I mean, technically I probably should have these identity symbols for this, but not too fussy about those kinds of things, okay? So what am I going to do for this? I'm going to start off by saying that z to the n plus 1 over z to the n is the same thing as z to the n plus z to the minus n. So this is, I will use the identity symbol because it's there. The first part is going to be a cos n theta plus I sine n theta. And then the second part is going to be a cos minus n theta, because as in minus n this time, plus I sine minus n theta. And if we're going to rewrite this, this one stays the same, this one stays the same, and we know from that line above that cos of minus n theta is the same as cos n theta, and this just changes it to a minus I sine n theta. So this one and this one cancels, and so we do end up with the expected part of the 2 cos n theta like this. And then there's a second part to the question that says, hence write this expression in terms of cosines. So I'm just going to kind of collect these two things together, and I'm going to factorize out a 3 for this. And what I mean is I'm going to collect this one and this one because they're both with powers of 5. and then this part and this part, they're already next to each other. So I'll do a little bit of rewriting for this. So it's a 3 lots of z to the 5 plus 1 over z to the 5 plus z squared plus 1 over z squared. That is just equal to, well, the thing that's inside the bracket, sometimes people forget they need to be the 2 there as well. So it's 3 lots of 2 cos 5 theta, just using those identities in the green box. And this one is just going to be a 2 cos 2 theta. So it is going to be 6 cos 5 theta plus 2 cos 2 theta. And we'll be using that in some of the next questions that we have as well. So the next thing I want to talk about is the first application of De Moivre's theorem. And I couldn't really think of a good way of expressing this, but it's basically when you're going from a sine or cos of something theta, and you want it to be in terms of powers of sine and cosine. Obviously, we do some where you go from powers of sine or cosine, and you want to write it back in that kind of form that we have here. So the way that we do these kinds of things for this one is we know this thing is true, right? When you take a complex number with magnitude 1 and you do it to the power of n, it is simply equal to just the arguments being multiplied by n like this. So to find cos n theta or sine n theta, you're going to use this thing. We're trying to find out what either of these parts here are. You're going to use binomial expansion on the left-hand side, and then you analyze the real or the imaginary parts to find out either cos n theta or sine n theta. Now, a little tip for you. I'm going to ask you to write this thing at the beginning to save some time. You can write down let c equal cos theta and s equal sine theta. It will save you a lot of time with writing things out. The only thing I'm going to say to be careful of is make sure that your s's are small and don't look like your 5s. I'll try and show you what I mean with that in my example. And then you need to replace high powers of sine or cosine using these identities, which are obviously our standard identities that we have probably learned in sort of year 12 in normal maths for this. So we're going to try and express sine 5 theta in terms of powers of sine theta. So I'm going to use this little green box at the top. That means we're going to be doing it to the power of 5, this thing, and we're going to try and pull out the imaginary part of it to find out what the sine 5 theta is going to be. So I know that cos of theta plus I sine theta to the power of 5 is equal to cos 5 theta plus I sine 5 theta. So now that I've got this expression, I know that the sine 5 theta, the thing that I'm looking for, is going to be the imaginary part of cos theta plus I sine theta to the power of 5. So I'm going to do the expansion on the cos theta plus I sine theta to the power of 5. But before I do that, I'm going to use my little tip, and I'm going to let c equal cos theta and s equal sine theta. It will be a huge time saver for this. So I'm now going to do my c plus is to the power of 5. I'm working on this expression that we've got here. And I'm just going to do the binomial expansion for this. Now, I personally, when I do this binomial expansion, I like to kind of write down a few things to kind of speed up the process. So I know it's power of 5. I'm a math teacher, so I know the coefficients, but you could grab these from either Pascal's triangle or your calculator. I know that it goes 1, then 5, then 10, then 10, then 5, then 1. But the other thing I like to do is to think about what the powers of I are going to be. So to begin with, we're going to have a c to the power of 5. There's going to be no i's in there at all, so it's just going to be a 1. But when I start introducing one of these, there will be an I. Next time there's going to be an is all squared, so there's going to be an I times I, which is a -1. Then you will have it being cubed. Then you'll have it to the power of 4. And then at the end, you will have it to the power of 5. Now, the reason I've put these things in is it should help me to find the coefficients really easily, because sometimes it's easy to forget about the imaginary parts that go with it. If you want to, you could do your c to the 5, c to the 4, c to the 3, and at the bottom you could do your s to the 5, s to the 4, like that as well, and you've kind of then got all of them in a line like this. Not necessary, perhaps, for everyone, but I really like doing this first and second column that we've got here. So the first one is going to be a c to the power of 5, and then my next one is going to be the 5 with the I, and then it will be a c to the 4 and an s. Notice my s is a little bit smaller. Now the next one, actually I don't know why I did a plus. The next one has a 10 and a -1. That's because we've got the I being multiplied by itself to get a minus. So it's going to be a -10 c cubed s squared. Then the next one is a -10i, looking from this expression that we've got here. I'm going to do the c down and the s up 1 power. And then we get a 5 just by itself with a c and an s to the 4. And then our last one is just going to be an I s to the power of 5 for that. And you might have other ways of how you want to do the binomial expansion, but I thought I would offer that up as a bit of a tip and put a little box around that so we know it's nothing to do with the question. So all we need to do now is figure out what the sine 5 theta part is going to be, and it's going to be the imaginary part of that expression. So this means that sine 5 theta is going to be the imaginary ones, which is this one, and this one. So jumping back to my pen, that means it's just going to be the 5. Obviously, we don't need the imaginary part because we're just looking at the remaining bits. And then there's going to be the minus 10 c squared sine cubed. And then we have a sine to the power of 5 for that last part. So now we're going to try and do this bit. We're going to replace the high powers of sine or cosine using these things. So this is a cosine to the power of 4. A cosine to the power of 4, well, a cosine squared is going to be a 1 minus sine squared. So cosine to the power of 4 is 1 minus sine squared, all squared. So we have a 5. I'm going to put the s right next to it. We're then going to have the 1 minus sine squared, all squared. And for the next part, I'm going to do my 10 with my s cubed, and then cos squared we know is just 1 minus sine squared. I'm converting them all to sines because the question said it wanted it only in powers of sine theta here, okay? Now it's just a bit of tidying things up, making sure you don't confuse your s's with 5s. So I have my 5s. This would be a 1 minus 2 sine squared plus sine to the 4. We then have for this bit a minus 10 sine cubed and a plus 10 sine to the 5 plus sine to the 5. Expanding these, it is a 5s minus 10s cubed plus 5s to the 5 minus 10s cubed plus 10s to the 5 plus s to the 5. And notice how all the powers are odd powers. That's very common for sine. If it was a cosine one, we would expect the powers to be, I imagine we expect the powers to be even, but basically you wouldn't expect a mixture of even and odd in these kinds of questions. So just kind of grouping them together, starting probably with the lowest power that we've got here. I think this is the only one that's just a single power, so it's just a 5 sine. And then it's the cubes next. So that's a minus 10 and a minus 10, so that's a minus 20 sine cubed. And then the powers of 5, there is a 5 and a 10 and a 1, which is a 16 sine to the power of 5. Now, unfortunately, that's not the end of the question. We do need to make sure that we go back and put it in its correct form by actually replacing the sines with what we said they were. So it's a 5 sine theta minus 20 sine cubed theta plus 16 sine to the power of 5 theta. Now, you probably know what the next question is going to be. It's the same thing, but kind of like the reverse process. So this time, we are going to take a power of sine or cosine, and we're going to write it in terms of sine nx or cos nx. In this case, cos 4 theta, cos 2 theta. No powers for these at all. Now, it's a slightly different approach for this, okay? We start off with using these facts that we had earlier on from de Moivre's theorem, okay? We know that this thing inside the bracket is 2 cos theta, and if I raise it to the power of n, well, then I know that this thing must also be true. So if I want to find out what cos to the power of n theta is, I can work on binomial expansion of this thing, and then just deal with this 2 to the n theta, 2 to the n at the end. Similarly, for sine theta, we could start off with the expression for sine, which is 2i sine theta. We can do some binomial expansion on this thing, and then if we want to find out what that is, we can divide it by the 2i to the power of n at the end. So that's what I've written here. Expand the left-hand side on this, simplify it using de Moivre's, and then either divide by the 2 to the n or the 2i, oh, excuse me, that should say to the power of n. I will change that in the PDF to find either the cos n theta or the sine n theta. And then an exam tip, it's possible that there will then be a follow-up question that uses the new form, whether that might be instead of trying to integrate this, they then ask you to use this form to do some integration. But I'm really trying to keep this as focused as possible on the complex numbers stuff that we've got here. So I will be using something like this. I know that this 2 cos theta to the power of 4 is going to be equal to this thing. So my 2 cos theta to the power of 4, that is my z plus 1 over z to the power of 4. Okay, so the left-hand side is going to be my 2 to the power of 4 cos to the power of 4 theta. And my right-hand side, I'm going to do some binomial expansion with this. Some people prefer to do this with the z plus z to the power of minus 1 to the power of 4. Quick reminder that the coefficients for the binomial of a power of 4, they go 1, 4, 6, 4, 1. Okay? So when I do the binomial on this, I will have z to the 4 plus 4 z cubed z to the minus 1. I then get a 6z squared z to the minus 2, a 4z z to the minus 3, and then to finish with a z to the minus 4 for this stuff. So then I can group these things together. So I have the z to the 4 and the z to the minus 4. This one goes with this one, and then we've got the remaining part just in the middle. So that's z to the 4 plus z to the minus 4. We then have 4 lots of z squared plus 4 lots of z to the minus 2. And then this is 6 lots of z to the 0, which is just a 6 that we've got here. So the first part, this is now, if I'm going to really spell this out loud and clear, this is this. The second part is 4 lots of z squared plus 1 over z squared. And the last part is a 6. And then if you're very familiar with De Moivre's theorem, we know that this is just going to be a 2 cos 4 theta, and this is a 2 cos 2 theta that we have here. So we have 2 cos 4 theta plus 4 lots of 2 cos 2 theta, which is 8 lots of cos 2 theta, plus 6. And then remember, we do need to divide by this 2 to the power of 4 here. We're actually currently working on 16 cos to the 4 theta. So this is my 16 cos to the 4 theta. We need to find out what cos to the 4 theta is. So cos to the 4 theta, I'll tell you what I'm going to do. I'll actually factorize out the 2 first, so that we have 2 lots of cos 4 theta plus 4 cos 2 theta plus 3. And then when I divide by the 16, I have the 2 divided by 16, which is an 1/8. So we have the cos 4 theta plus 4 cos 2 theta plus 3. Okay. And then again, this is the part they might ask you to do some kind of like integration step that might be going with this one. Okay, next up is realizing the denominator for some more complex expressions. And this is kind of like a skill that I want to do that will help us to answer some questions about sums of infinite series. But I think this is something that I've like touched on in my playlist of videos, and I wanted to kind of use this as an opportunity to explain a little bit more about this so that we have an idea of like how to approach these kinds of questions. Now, when I'm talking about realizing the denominator, when we have expressions that look like this, or any of these three that we've got here, it really is about trying to make this something that we can actually work with. And actually by making the denominator a real number, we can actually deal with more kind of processing, more kind of skills that we want to do with this. So let's just talk through these things that I've got in the box over here. So we often want to make a denominator real to better analyze an expression. If the denominator looks like this, where these two things here, a and b, are different to each other, its conjugate is the same expression, but just with the power negated. So we've got a new kind of definition of what we mean by a conjugate in this kind of scenario here. The same expression with a negated power. The method of multiplying the numerator and denominator by the conjugate will always realize the denominator. And of course, if you're multiplying the numerator and denominator by the same thing, it's like multiplying by 1, so we're not actually changing what it does. Now, in some cases, another option may be desirable. This is something that I've learned that the name for this is called the phase factor. What it is a single exponential expression that centers the angle of the expression back to 0. Now, this phase factor will only work on expressions of this form, where it is a plus a e to the c I theta. In other words, these two numbers have to be the same as each other. The conjugate one will work for any of the expressions. The phase factor will only work for this one. And actually, if it is in this form, you have a choice between using the conjugate or the phase factor. And I'll explain a bit more about why you might pick one of them over the other one. So for this phase factor, what it actually ends up being is you just multiply by this, okay? So it's an exponential with modulus 1 with a negated halved power. So whatever this power is, you negate it, meaning negative to positive or positive to negative, and you half it. And I will show you what that does in just a moment. But it basically gives this one and this one the same power, but one is positive and one is negative. So you can use De Moivre's theorem. Now, this can be desirable for certain kinds of questions, but the majority of the time, the conjugate is the one that you're going to need, and the conjugate works for absolutely any expression in the denominator. Okay? So let's try and realize the denominator for this expression that we've got here. And we'll notice there's a 4 here and not here, so we don't have an option. We have to use the conjugate for this question. Now, the conjugate is the same expression as the denominator, like this, but we just negate the power. So it's going to be a 4 minus e to the minus 3i theta. I don't know why I still find by putting brackets, it just reminds me we are doing a double bracket expansion here. Now I'll do the numerator in just a second, because the thing I'm really interested in is the denominator. So we'll have the 4 and the 4, which gives me the 16. And then I like to do these two, because you have this power and this power, they give you a power of 0. So overall you end up with something that is just a 1, and you have a negative times a negative, so there is just a positive 1 for this part that we've got here. Then we get, for this one with the positive power, we get a minus 4 e to the 3i theta, and then we get a minus 4 e to the minus 3i theta, okay? I'll do the numerator, but really the denominator is the thing we're most interested in here. The 2 and the 4 gives us the 8. We then have a 4 times a minus 3, so that's a minus 12 e to the 5i theta. And then we'll do the minus 2 e to the minus 3i theta. And then these last two things multiplying gives us a plus 3 e to the 5 minus 3 is 2i theta, like this, okay? So let's continue working on what we've got at the bottom here. The numerator, like I've said, is something we will deal with later on in the question. But we're trying to make the denominator real, and actually we should recognize that the denominator is now 17 minus 4 lots of e to the 3i theta plus e to the minus 3i theta. And this is a form of, like, De Moivre's theorem that we've got here. So we should know that this expression that we've got can be written like this. Here we go. It's like the same as the kind of z to the power of 3 plus z to the power of minus 3. So that whole expression that's here is the same as 2 cos 3 theta. So this is the same as 2 cos 3 theta, meaning if we finish this off, we still have that long, ugly bit in the numerator for now. But the denominator is now something really neat, and it is just the 17 minus 8 cos 3 theta. So you're going to get really good at spotting these patterns. With a plus, it's a cosine. With a minus, it's a sine. And really, it's just a variation of this kind of thing that we're using here, apart from it's obviously instead of z form, it's an exponential form instead. Now, this is the one I kind of wanted to show you a little bit more about, because this expression has a same number here and here, okay? The conjugate is going to give us something that's kind of similar to this one. I'll show you what happens when we do the phase factor with this as well. So to multiply by the conjugate, it is going to be the exact same expression, but with the power negated. So that's going to be to a 4i theta, and this is going to be a 3 minus 3e to the 4i theta. So the numerator is nice and quick. It is going to be a 6e to the I theta minus a 6e to the 5i theta. A little bit quicker this time. The 3 and the 3 gives me a 9. This one times by this one, the power is 0, so it's just going to be a 1. But you have a minus 3 and a minus 3, so we get another 9 here. Now we get, for the other parts of the brackets expanding, we get a minus 9e to the 4i theta and a minus 9e to the minus 4i theta. So continuing with this, numerator, don't worry ourselves about it for now. Denominator, though, is an 18 minus 9 lots of e to the 4i theta plus e to the minus 4i theta. If there was a minus in between, it would go to a sine, but there isn't. It's going to go straight to a cosine. So that means we have in the denominator an 18 minus 9 lots of 2 cos 4 theta. Let's just save ourselves a bit of time. Let's just change this to an 18 cos 4 theta, okay? So it's 18 minus 18 cos 4 theta. Notice something here. This is what I want to try and use this video as a quick opportunity to do. The power here is like a 4 theta, and we end up with a 4 theta in the denominator. So there's a kind of clue. Conjugate will always give us that same idea. We have a 3 theta and a 3 theta here as well. When you do the phase factor, something different happens. So the phase factor says to multiply it by an e with a negated halved power. So it's going to be an e with a negated halved power. So let's see what happens. Numerator I'm not bothered about. It's going to be a 2e to the 3i theta. the denominator is a 3e to the 2i theta. So I've now just given this an angle of a 2 theta. This one is now going to go from a minus 4i. I'm going to give it 2 more. It's going to go to a minus 2i. So we get a minus 3e to the minus 2i theta. This is what I meant about it centering the angle of the expression back to 0. In between the 2i theta and the minus 2i theta is the 0. And we've now got ourselves an expression that is very, very easy to simplify, because it is 2e to the 3i theta over 3 lots of this thing, which is something we very quickly recognize as a sine expression. So this is 3 lots of times 2i sine 2 theta, like this. So let's just continue with this a little bit more. That's 2e to the 3i theta over 6i sine 2 theta. Yes, we wanted to realize the denominator, and we've got an imaginary number in there. So let's just multiply this by I and I. So the numerator is 2i e to the 3i theta. The denominator is going to have an I times an I, which gives us a negative. So overall, I'll just make sure that the thing is now negative, and we get 6 sine 2 theta. So the weird thing about this is that this expression that we have here and this expression that we have here are exactly the same as each other. Very, very strange. So the little note I put here, notice the difference between the arguments and the denominator. One is halved and one is as before. This one is as before, 4 theta and 4 theta. Here, there was a 4 theta and it has become a 2 theta for this question. So it may be desirable to do this. This is super niche, but I wanted to add it in to this video. So let's apply this. We're going to do some sums of infinite series. First thing we're going to do, convert this thing that we've got here into exponential form. This thing that we've got here, excuse me. That's my preference. You can do it other ways. I like doing exponential form. You then use your sum of infinite series formula. You realize the denominator, and then you analyze it for real and imaginary parts for these kinds of questions that we have here. Okay. So this one says we've got the infinite series C and S are defined by this and this thing. Given that they are both convergent, show that C plus IS is equal to this expression. So let's actually begin and say to ourselves, well, what is C plus IS? It is going to be a cos theta. I'm actually going to just start multiplying these things. They kind of look like they're coming in like groups like this. So instead of writing out all of the C ones and then all of the sine ones, I think it makes more sense to kind of do them in those groups. So there'll be a cos theta plus I sine theta. Then the cos 2 theta is going to go with the minus I sine 2 theta. Then a cos 5 theta and a minus I sine 5 theta. I'm just going to kind of stop there because you can see the rest are just going to keep going and going as well. Some of these are going to need to convert because there's negatives, which we don't usually like for this kind of stuff. So we have a cos theta plus I sine theta. The next part will be a cos of minus 2 theta plus I sine of minus 2 theta. And then we have a cos of minus 5 theta plus I sine of minus 5 theta. Now we've got it written in this kind of form. The first step I said was to convert it to exponential. So we have e to the I theta. Then we have e to the minus 2i theta. Then we have e to the minus 5i theta. If we wanted to, the next one would be e to the minus 8i theta. And that just keeps going. So this is a type of series that we've got here. This is a geometric series. And the next step is this, to use the sum of an infinite series formula that we have for this. So we're going to say that the sum to infinity sum, I'm avoiding using s with the infinity because s is representing something different here. We know that the formula for this is a over 1 minus r. A is the first term in the series, which is e to the I theta. And the common ratio is what we're multiplying by each time to move it along. And you should be able to tell that this is e to the minus 3i theta. So this means that c plus is is equal to e to the I theta over 1 minus e to the minus 3i theta, which is exactly the thing that they wanted us to show being true in the first part of the question. Part B then says, hence show that the cosine part is this. Let's remind us of what we're going to do. We're now going to realise the denominator and we will analyse for the real and imaginary parts. Well, if we're looking for C, we're going to look for the real part of this thing that we have got here. So I'm going to realise this denominator. Now we have a choice because there is a 1 and a 1 here, meaning we can either do the conjugate or the phase factor. But look at the angle that we're aiming for in the question. There is a 3 theta here and there is a minus 3 theta here. That just seems like we're going to do the classic easy one of the conjugate, and we'll just kind of go from there. Okay, so we're going to multiply by the conjugate for this. Okay, so we have now that C plus IS is going to be that thing. So C plus IS is going to be the e to the I theta over 1 minus e to the minus 3 I theta multiplied by the conjugate. That's 1 minus e to the positive version of that. Same expression, but just with the power change. Now, we've done a lot of these, so I'm not going to spend too long on this. That's e to the I theta minus e to the 4 I theta, like this. And for the denominator, we get the 1 times the 1. We then get the 2e expressions, which gives us another 1. And we'd have minus e to the 3 I theta minus e to the minus 3 I theta, like this. So we end up with e to the I theta minus e to the 4 I theta over 2 minus 2 cos 3 theta, like this. So I'm going to try and find out what the cosine part is by finding just the real part. If I'm going to try and find the real part, I'm now going to do something I didn't do in the previous part, which is to kind of write these in their trig form that we're looking for. So that will be a cos theta plus I sine theta minus a cos 4 theta minus I sine 4 theta, all divided by 2 minus 2 cos 3 theta. And we are looking for, as I said before, the real part, not the imaginary part. And the real part is this and this, still with that same denominator. If we wanted to find out what sine was equal to, are we going to do that in the next part? Yeah, we'll do that in the next part of the question as well. So this means, hence, C is equal to cos theta minus cos 4 theta over 2 minus 2 cos 3 theta. And then for part C of the question, we're going to say what sine is equal to. So we will sine is going to say the imaginary part. And the imaginary part in this question, if I use a different colour, is this part and this part, making sure you take the negative and still with that same denominator. So hence S is equal to sine theta minus sine 4 theta over 2 minus 2 cos 3 theta. Last thing on this kind of thing, what about if the same question had this part B instead? So instead of saying show that cos is equal to this expression, if it said show that cos is equal to this expression, what would we be looking at doing instead for this one? So look at what's happened to the angle that we've got. The angle has been halved, okay? We've got something with a 3 and it's now a 3 over 2. This seems like they would be encouraging us to use the phase factor. I haven't seen a question like this, but I just think it was kind of worth us thinking about how these things could play out, okay? So let's go back and do the realizing. We have that C plus IS is e to the I theta over 1 minus e to the minus 3I theta. We're going to do the power negated and halved. So that is going to be e to the minus 3, not negated and halved, I actually need to negate it. So it's this multiplied by this. The numerator becomes e to the 1 theta plus 3 over 2 I theta is 5 over 2 I theta. And then the denominator that we have is going to be e to the 3 over 2 I theta minus e to the minus 3 over 2 I theta. So we have, for the numerator, a cos 5 over 2 theta plus I sine 5 over 2 theta, all divided by, now that denominator is going to be a 2I sine 3 over 2 theta. I think there might be a little typo in the question, so I will have changed it in the PDF, okay? So we are now looking for what the imaginary part of this is going to be. Well, let's just multiply, get rid of this I that we have down here. let's multiply the top and bottom by I. So we then have I cos 5 over 2 theta. I times I is minus sine 5 over 2 theta. And then the denominator is going to be 2 sine 3 over 2 theta. But the overall thing then becomes negative. So if we're looking for the cosine part of this, the cosine part of this is the real part. So this is the real part, and this is the real part. No, there wasn't a typo in the question because those negatives did cancel out with each other. So we end up with, hence C is the real part. So C is equal to minus sine 5 over 2 theta over minus 2 sine 3 over 2 theta, which is just sine 5 over 2 theta over 2 sine 3 over 2 theta. Now, again, they haven't asked anything like this before, but I just wanted to make sure that we were like fully prepared for these kinds of things. And I wanted to kind of give you a bit more of an idea about what we mean by this, this phase factor and how we can decide when we need to use it and when we don't need to use it. Okay, next up is roots of complex numbers. Try and go a little bit quicker through this because I know this is a long video. 4 roots of unity, meaning when something is just equal to 1, unity meaning 1 that we have here. If we have z to the power of 1 being equal to 1, the roots would be 1, omega, omega squared, all the way up to omega to the power of n minus 1. Basically just saying each time you multiply by the same thing to get the next root. There is a fact about this, that the sum of the roots of unity is equal to 0. Okay, the sum of the roots of unity is equal to 0 that we have here. I couldn't write a question that included this. It's very rare for them to use it. When it has been used in the textbook, it's basically the only questions I could come up with were the same ones. If you have roots of complex numbers, so instead of z to the power of n being equal to 1, z to the power of n equals k, where k is a complex number, still, the roots will form the vertices of a regular n-gon, like a n-sided polygon, i.e. they have equal angular rotation between neighbouring roots. And that's the same thing with roots of unity as well that we have there, okay? So, we'll start off with this one, with a roots of unity question that we have, which is a z to the power of 5 equals 1. Determine the roots of this, showing them on an argand diagram. Well, we know that one of the roots for this, when we have z to the power of 5 equals 1, well, one of the roots has obviously just got to be equal to 1/5 rooted, which is just going to be 1. And then each time we want it to move around the argand diagram so that they are equally spaced out angularly. There's 1 starting here. I want them to move out so that they spread like 1, 2, 3, 4, 5 like this, meaning that each of those angles kind of spreads it around. So the whole angle that we have for the entire sort of circle or the entire argand diagram is 2 pi. Because we want it to be for 5 roots, it would be split between 5. So each time we are going to move it around the argument by 2 pi over 5. The first one, you can kind of imagine it, it's like e to the power of 0 I, like this. We're just going to call it 1. So the next one, when we multiply it by e to the 2 pi over 5, 2 over 5 pi I. The next one would be e to the 4 over 5 pi I. E to the 6 over 5 pi I. And then e to the 8 over 5 pi I. If we did do the next one, if we multiplied again by e to the 2 pi over 5 I, we would get e to the 10 over 5 pi I. 10 over 5 is 2, you get 2 pi I, which is a full rotation, and we are now talking about that same complex number that we've got here. So with these roots, like we've said for this one too, it forms a regular polygon. In this case, it has formed a regular pentagon, where this one has an angle of 0, 2 pi over 5 I, 2 pi over 5, 4 pi over 5, 6 pi over 5, and 8 pi over 5, okay? So we're now going to do a different question where we are going to be doing it where this is a complex number instead. It is cubed, so we know it's going to be like a triangle, and instead of it moving 2 pi over 5 each time, it's going to move 2 pi over 3, okay? They want the roots given in this r e to the I theta. And I've said this, to move from one vertex to the next, you increase the argument by 2 pi over n, i.e. you multiply by e to the 2 pi over ni, where n is obviously this power that we've got here. So I think probably the best thing is to get this into some kind of exponential form to begin with. So when we have our z cubed equals 4 root 2 plus 4 root 2i, well, even kind of sketching that, it's pretty obvious what the argument is going to be. It's 4 root 2 and 4 root 2. That has to be pi over 4 because you have an isosceles right-angled triangle there. So the argument is going to be pi over 4 I theta. And then I think, not I theta, just pi over 4i. And then what else do we need? The magnitude of this. So if I find the magnitude, it will be the square root of 4 root 2 squared plus 4 root 2 squared. So I'll do that very lazily on my calculator. 4 root 2 squared times 2 square rooted is 8. So putting it in exponential form, it's equal to this. Let's find the first one by just doing the cube root of both of this thing and this thing. So that's 8 to the power of a third. And e to the power of pi over 4i to the power of a third. That means my first complex number is going to be 2, the cube root of 8. And then we get e to the pi over 12i. So now I want to find out what the next complex number is. Well, we just want to move it around the circle so that we get a triangle. We're going to be multiplying it by this expression each time. So it's a it's something that's got to the power of 3 in this question. So we're going to be multiplying it each time by e to the 2 pi over 3i. In other words, this argument is going to increase by 2 pi over 3. So that's 1 over 12 plus 2 over 3. That's 3/4. So the next one has just moved around like this. And then if I add on another 2/3 by multiplying here, the next one is 17 over 12. So it's 17 over 12 pi I. If I do multiply it one more time, I go to 25 over 12 pi I. But that is the same as this one. 25 over 12 minus 2 pi. And you go back to a 12th for this one. I just want to double check that we've got it in the form the question wanted. They wanted it between 0 and 2 pi. All three of those are between 0 and 2 pi. As well for this. If you were to plot this on an Argand diagram, which I will do very, very quickly, the first one is at pi over 12, the second one would be at 3/4, the third one will be somewhere down here, and it has actually formed an equilateral triangle where all of these lines are 2, okay? This is a long video, so I'll try and do this one a little bit quicker for our very last example that we've got here. It says, the point represented by this complex number is one vertex of a regular hexagon. Find the 5 other points as complex numbers in a plus bi form that we've got here. So they've already given us a root this time. We're not actually having to do any rooting. This just means that we need to kind of move it round by 2 pi over 6 radians for the next root. Okay, so what this is actually saying is we're going to be multiplying it by e to the 2 pi over 6 is pi over 3i for this case. So z1 is equal to 3 minus 2i root 3. Now actually your calculator is going to be able to handle this. So this is going to be e to the pi over 3i just multiplied by 3 minus 2i root 3. Don't need to even put it back into, I mean, if you want to, you could put this into exponential form because it just wants the answers. I'm actually just going to put this all into the calculator and speed up this and show you that the calculator is quite powerful. So I'm going to type this 3 minus 2 root 3i, and then I'm multiplying that by e to the, I'm doing that as answer, times e to the pi I minus, pi I divided by 3. Okay. So when I press equals, it gives me my next answer, which is a 9 over 2 plus root 3 over 2i. My third root, when I press equals again, is going to give me 3 over 2 plus 5 root 3 over 2i. My next one is minus 3 plus 2 root 3i. And then my fifth one is minus 9 over 2 minus root 3 over 2i, and my last one is minus 3 over 2 minus 5 root 3 over 2i. And geometrically you can see that this one and this one are opposite each other, because if these are positives and these are negatives, we can see that this one must be opposite this one, and this second one must be opposite this fifth one that we've got here. So they sometimes ask you that, and actually you can see if you were to sum up all of these roots, they would also come to 0, because you can see the opposite pairs sum to 0. So this part here also holds true for this type of question as well. Okay, one last thing that is not really covered in the textbook or the specification, but again, I wanted to use this as a quick opportunity to do some teaching, even though I know this has been a long video, is some questions they've asked about recently have them looking like this. They have like z minus some complex number to the power of n is some other complex number to the power of n as well, where alpha and beta are complex numbers. What happens in this is a different kind of representation of a regular polygon. The roots of z represent the vertices of a regular n-sided polygon centered at alpha. And this kind of reminds us of complex numbers, I don't know, where we had things like z minus z1 equals r. It's like a circle that was centered at z1. It's like the same thing. We're now going to have a polygon that is centered at alpha. But there's a little extra bit that I've put down here that is definitely beyond the specification. Beta, what it does, it enlarges the polygon by a scale factor of the magnitude of that complex number, and it does some rotation to the polygon as well. So alpha changes the center, and B kind of does a bit of a scaling and a rotation. If you're interested, you can think why it is this. It does a rotation of the argument of B divided by n, but it is definitely beyond the specification. But they have started asking questions that look kind of like this. So this question says, what is the geometric interpretation of the roots of the following equation? So it's going to be a power of 4 that we've got here. So I definitely know that this is going to be something to do with a square. I'm going to do a little bit of rearranging so that it's just equal to 16. And this thing to do with this minus alpha that we've got here, this is actually going to tell us where the center of this square is. So I can say that it is centered at 0, 1, because obviously that's I being represented as 0, 1 here. And then we can actually tell something to do with the scaling, because this is b to the power of n. This is 2 to the power of 4, right? This is 2 to the power of 4. So this is actually representing some kind of scaling that we've got here. And because of this feature, there's actually no rotation at all in this question. You would never need to answer this kind of question, but hopefully this might kind of deepen some of your understanding that you've got. If you were going to go about just solving this question, we can then see that z minus I is equal to just 2. But if I was going to find out what the other values are, we would increase it by pi over 2 each time. So you get 2e to the pi over 2i, 2e to the pi I, and then 2e pi over 2 each time? Yes. And then 2e to the 3 over 2 pi I, which works out as 2i minus 2 and minus 2i, meaning our solutions are 2 plus I, 3i, minus 2 plus I, and minus I that you've got there. If you were to put all of these coordinates onto an Argand diagram, I guarantee it would be a square centered at 0, 1 and scaled up by 2 from the original kind of square that we've got at these coordinates. Now that was only a bonus question just because they've started asking some things like this, and I thought it might be useful to kind of think through some of that stuff that we've got there. I apologize because this is a long video, but I think complex numbers, as kind of described by the title, is a very complicated topic that we've got there. So I hope this is helpful for your revision, and I hope to see you in another video sometime soon.